In this last video of section 2.1, we're going to get into the real meat and potatoes of the section. So far, it's been a lot of notation. We have like definitions of linear transformations, and we defined matrix by vector multiplication and all that. So it's a lot of terminology to learn. That doesn't necessarily make it easy, but there hasn't been a lot of like depth and complexity going on. Now we're going to get into stuff that's a little trickier. So, example 8 is going to be an example of like why this next theorem works. We'll actually prove the theorem too, but I think this example helps understand it and put it in some context. And then we'll also do a couple other examples of using that theorem. So this says we have the set of points S here. It's a set of x1, x2 points where the x1 is in between 0 and 1, and likewise x2 is also in between 0 and 1. And we can call that the unit square. Now, we're also going to have a transformation, t of x, defined by multiplication by this matrix A here. And we're going to describe the set of output points we get given input points that are in the set S inside the unit square. So the first thing we're going to do is a good way to think about this is a trick you might not think of. First of all, the vector E1 just means the point 1, 0. Likewise, the vector E2 points at the point 0, 1. And you could think of it as the arrow or as the point, whichever one makes more sense. And what we're going to do is notice that any point x in S means that x can be written like so. Let's write it as x1, x2 as a vector. That's the same thing as doing x1 times the vector 1, 0 plus x2 times the vector 0, 1, right? Because if you do this linear combination out, you just get x1, x2. And we also know we can write that as x1, e1 plus x2, e2. So, for example, if we had the point right here, let's say, which is like 0.2, comma 0.6, something like that. We can think of that as 0.2 times E1 plus 0.6 times E2. Same idea as doing this linear combination of those. Okay, now you're probably thinking, why are we bothering to do this? Well, because we know that t of x is a matrix multiplication transformation, we showed that it is a linear transformation, satisfies the distributive rule and the associative rule that we want. So the output, t of x, can be written t of x1, e1 plus x2, e2. And because it's linear, we can use the distributive rule. We can like distribute the t into these two terms, and then we can take out the scalar multiple of x1 and x2. Like so. And if we're restricting x to be in S in this unit square, that's the same thing as saying that x1 and x2 are between 0 and 1. So this is what we want to describe is the set of vectors that can be written as linear combinations of t of e1 and t of e2, where the weights are any numbers between 0 and 1. So what we need is we need t of e1 and t of e2. So let's go ahead and actually look at the matrix to see what those are. So first of all, t of e1 means we're going to multiply the matrix A by e1, which is the vector 1, 0. And this, by definition, means the linear combination of the columns of A using 1 and 0 as weights. And what you get is the vector 1, negative 2. Likewise, t of e2 uses 0 and 1 as weights, and what we get is just 0 times that first column plus 1 times the second column of A, which is just 0, 1. So t of e2 is actually equal to e2 in this case. Okay, so to put this all together, what we're talking about when we talk about this set is the set of these linear combinations, but replacing the t of e1 with the result 1, negative 2, and t of e2 here with its result 0, 1, we get the following description. So this is the set of all linear combinations of the vectors 1, negative 2, and 0, 1 using any numbers between 0 and 1 as weights. So what does that look like? Let's draw a picture. Right here is the point t of e1, and right here is the point t of e2. And when we get all such linear combinations of these, that includes like 0 times one of them plus 1 times the other, which would just be the 2 points we have, or x1 and x2 could be 0, right? The origin is right here. And if you do 0 times 1 plus the other, t of 0 is still 0 right here. Or you could do 1 times t of e1 plus 1 times t of e2, and you get the vector 1, negative 1. Of course, that's what you would get when you connect these tip to tail, like so. So you end up at that point on the parallelogram. And if you take something like in between, like if x is 0.2, 0.6, what you'd get is something like part way down this one, 0.2 of the way down that one, plus 0.6 the other one, which might put you around there. And any other point in between, like in the middle of the square, is likewise going to give you another point in the middle of this parallelogram. So that is how you can describe the set t of x such that x is in S. It's the parallelogram determined by t of e1 and e2, where two of the adjacent sides are t of e1 and t of e2. All right. This is a situation where I'm glad I can do this in a YouTube video, because getting all these colors right took me 20 minutes to do this example. This is how long the video at this point is 20 minutes long that I've recorded. Later I'm going to edit it down. Might be less than 10 minutes because I spent so long fumbling with all the different keyboard shortcuts for the colors. So yeah, I'm glad I can edit that down and not waste all your time where you watch me fumble. Anyways, this is sort of an illustration of why theorem 2.4 works. This says that if t from RC to RR is a linear transformation, then t of x is equal to this matrix times x, where all the columns are t of E1, yada yada, up to t of EC. And the result is that linear combination of those columns using the entries in x as weights. And this matrix is called the standard matrix of T. So this, by the way, before we actually prove it, I just want to point out that now we're saying that every linear transformation is actually a matrix transformation too. So linear transformations and matrix transformations are really the same, but they're two different ways of looking at it. One is as a transformation that satisfies these properties. Any transformation that satisfies these properties is linear, but you could also write it as t of x equals ax. Now, to prove this, we're going to say that x is any vector in RC, which means it has c components, and you can write it like this. We're going to take t of that x, but writing x as a vector like so means that we can write it as x1 times 1, 0, 0 plus x2 times 0, 1, 0, 0, 0, but I'm not going to bother writing that, plus xc times 0, 0, all the way through 1. And this means x1 times e1, yada, 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 up to xc times ec. Now at this point, we can see that any vector x is really a linear combination of these identity matrix vectors. And because t is linear, it has these properties, a distributive property and an associative property. And this is a linear combination of these vectors of the form t of e1 through t of ec using the entries in x as weight. So that's what the right side of this is. And at this point, we can just apply the definition of matrix by vector multiplication, where we're taking the matrix that has columns like so and multiplying that by the matrix x1 through xc. And maybe we should just label these steps to be formal. I didn't actually write this, but we're assuming that t is a linear transformation. So this is using the definition of linearity. And from here to here, we're using the definition of matrix vector multiplication. So yeah, that proves the theorem. T of x can be written like that. And this defines also what we mean by the standard matrix of any linear transformation. All right, let's look at example 9. T from R2 to R2 reflects points across the x2 axis. Find the standard matrix of T and check that it works with a couple points. Okay, so the standard matrix of T is T of E1 and T of E2 are going to be the columns. And at this point, by the way, I'm going to give up on this color scheme. That was taking too much mental effort to keep that up. So what is T of E1 and T of E2 if T reflects points across the x2 axis? Here's the point E1. Here's the point E2. Here's the x2 axis and the x1 axis. So reflecting points across the x2 axis means we're going to flip them across this line and they're going to end up over here, like the same distance away. So here's T of E1. It's been reflected across. It's now at the point -1, 0. And T of E2, it's on the x2 axis, so it doesn't move anywhere. It stays in the same spot. Sort of like when you look so closely in a mirror that you like stick your nose against the mirror. That's where T of E2 is, touching the mirror so it doesn't move. Okay, let's find what this actual matrix is now. So T of E1 is now -1, 0, and T of E2 is still 0, 1. So that should be the standard matrix of T. Let's check that it works with a couple points. Like, let's say, I don't know, over here is a point 0.5, -2, something like that. So if that's x, what T of x should be is it should be reflected across. It should be down here. It should be now -0.5 and -2. X2 coordinate is the same. It's still at the same height. It's just moved to the opposite side of the x1 axis. We want to check that if we do this matrix with columns -1, 0 and 0, 1, that we get what we should. And that's going to come out to be -0.5, -2, which is what it should be. All right, it says check that it works with a couple points. Here's another point, 0, 0. We'll make this one easy. If that is on the x2 axis, it shouldn't go anywhere when it's reflected across. So T of 0 should still be the origin. T of 0, 0, if the standard matrix is correct, should be this matrix multiplied by 0, 0. And of course, that's going to give you a linear combination where the weights are 0, which, yeah, is always going to be 0. Okay, so we checked it with a couple points. So let's put a box around our answer. There's our standard matrix. Let's look at example 10. In this case, R sub phi rotates points an angle of phi counterclockwise around the origin. And it turns out this is a linear transformation, but how can we write it as a matrix transformation? What is the standard matrix for it? So just so we don't have to draw difficult pictures here, we get a head start with this nice graph. So this is the angle phi that everything is rotating. In the picture, it looks like it's about 30 degrees or something like that. But this should work no matter what phi is. This started from the point E1 here. And if you're just rotating it by an angle, this distance, the length of that arrow should still be 1. So this should be a point on the unit circle. Now, the point on the unit circle is the definition of sine and cosine. The x-coordinate here is the definition of cosine of phi, and the y-coordinate of this is a definition of sine of phi, like so. Okay. With E2, here's where E2 started at the point 0, 1. Again, this is still a distance 1. So this point T of E2 is still on the unit circle, a distance 1 away from the origin. It's just been rotated. But this one's a little different. There's a few ways you can think of it. You could notice that this triangle here is similar to, or is congruent to this triangle over here. So the length of the shorter side is going to be the length of this, which is sine of phi. It's just that now the x-coordinate is negative, so it's actually at the opposite of that. And likewise, the y-coordinate, how long this vertical thing is here, is the length of the longer side of this congruent triangle, which has length cosine of phi. So this y-coordinate is positive, and that's cosine of phi. And that basically works. It's a little bit sloppy because I'm assuming that this is that the angle phi here is in quadrant 1 in order to say that T of E2 is going to be in quadrant 2 with negative numbers, and this picture might not look the same way if phi was something like 400,000,002 degrees. So to be a little bit more formal, we can say that T of E2 has coordinates that are defined by this bigger angle here, which is 90 degrees plus phi, and the x and y coordinates are going to be still going to be cosine and sine of that standard position angle. And there's a trig identity that says that cosine of 90 degrees plus phi is always equal to negative sine of phi, and sine of 90 degrees plus phi is always equal to cosine of phi. Yeah. Okay, so either way you want to think about the second one, the standard matrix A that has these as its columns looks like so. Okay, so let's check that this matrix of this kind of linear transformation works specifically if the phi is 2 pi over 3. So 2 pi over 3 looks like this. So we started with E1 would be here, and when it gets rotated to be at this point, we're talking about that, and E2 started on the x2 axis, and it's also getting rotated to end up here. Now let's check that this formula works. Now cosine of 2 pi over 3 is negative 1/2, and sine of 2 pi over 3 is root 3 over 2. And just to check that we have the right signs everywhere, yeah, T of E1 looks like its x-coordinate should be negative, and its y-coordinate should be positive and a little bit bigger than the x-coordinate. And likewise, T of E2 looks like they both should be negative, and the x1 coordinate is a little bit bigger than the x2 coordinate. So yeah, just a reality check there. Now, let's check that this works for the point x equals 1 root 3. So that point is right here. And the reason we're doing this point is it's kind of a special point because it turns out it's actually already at an angle of pi over 3. Like, for example, if you're going to do tangent of pi over 3, you would get root 3 over 1. And if you're going to do sine of pi over 3, that is, of course, root 3 over 2. And the y coordinate here is root 3. And if you use a Pythagorean theorem, you get the distance is 2. So yeah, that's the angle that this is at. And that's nice because if this gets rotated by another 2 pi over 3, it will end up at an angle of pi. And if it's staying the same distance 2 away from the origin, we're talking about this point, -2, 0. Let's check that that's what we get. Okay, so using the matrix here, we want to see if this linear combination comes out to be that. So let's work it out. And sure enough, this linear combination works out to be -2 as the first component, and the second component is 0. Yay. Okay, so it looks like it works, but I also want to use this as like an illustration of how linear transformations work, which is that there's a reason I drew this like whole grid here to go with this. What I mean by that is this linear combination we just did, well, we started with an x1 component of 1, right? That's this 1 here. That gets multiplied by t of e1. So we did t of e1 times 1. The x2 component is the square root of 3. If you do that square root of 3 times t of e2, it's like you're adding this vector here. And the components of the vector that you start with, the x, tell you where the output is going to be on this rotated grid. We could take another example really quick. Let's say that z is over here. Z has regular old coordinates 2 and -1. What I'm trying to say is we could use these regular components 2 and -1 as coordinates along the rotated grid we have here. So if we go 2 units in the direction of t of e1 and -1 units in the direction of t of e2, that's like this way, that will get you a point over here, like so. Now, this grid is getting kind of messy. I don't think it would help too much if I drew more examples here. But if you want a better illustrated explanation of this, there's a really good 3 blue, 1 brown video. I'll put a link in the description of this. And all right, that is section 2.1. This idea of linear transformations as matrix multiplication is a key idea. We are going to continue thinking about matrices as their own mathematical object that has certain kinds of properties, like this distributive property we looked at before. So, yeah, I will see you later.